All right, so the test was a thing that occurred. This is the best that can be said for it. It is a thing that happened. Um, so let me sit down here. I'm all by myself again. Um, I don't know what happened. So I know that some of it was um, on me, maybe not kind of imparting some things clear enough. So, for example, one second. Um, Let me fix this. So, like, maybe I didn't do a good enough job impressing or imparting that. Let's say we have, you know, right. Let's say you have an example. I know I have the fat thing. Uh oh. And then I locked Corey out. All right. Sure. There's somebody to like unlock that. Um, right. So maybe I did a bad job, like imparting that. Let's say you have an aldehyde, and you have a Hornwise with image reagent, right? Which got really sketchy there. Right. And then, right, for this reaction to work, you need a base, right? And then it's going to make a transferable bond, right? Maybe I did a bad job of kind of letting you know that, this base can be almost any base. So where you may have had an example that was, you know, this, I'm going to pretend this all fits really hard. I'm going to pretend. Right. Or we have an example where we have this and sodium HMDS, right? Where this is just a base, and you get the reaction. Right? And then if I do something that's a little different, right, where I still have an aldehyde, the Horner-Wasson image reagent, and a different base, that the reaction still works. Because I think a lot of people got hung up on just that they didn't see one exactly like they saw in their notes, so then they didn't know what to do with things, or didn't know what to do with it. And like that could be on me, um, by not kind of clearly pointing out that, hey, now here's a different aldehyde, a different, right, Horner-Wasson image reagent, like it's an ethyl group and it's got a methyl here and it's a different base, right? But at the end of the day, it's still going to make a double bond because it's still the Horner-Wasson image reagent. The base, or a base, and an aldehyde. So I think that maybe I didn't do enough like straightforward examples to kind of illustrate that, hey, um, um, just because you change a base, like the fundamental, if the conditions change some, the fundamental thing that reagent does is still the thing that reagent does, right? It doesn't change the reaction. The base can change the selectivity a little bit, or can change the rate, but at the end of the day, it's still the same reaction that's happening. Like the big overarching reaction is the same, and making those changes of base or whatever are things that are done to optimize the reaction, right? Where you, as I roll away here, I got one person here, so I'm trying to have the computer screen not block them, right? So you have the situation where these things are optimizations. We're going from N-butyllithium to sodium HMDS to LDA. The base might change the yield of the reaction, right? Because the people had to, like, in a real sense, optimize the reaction to make it work the best it can. But at the end of the day, it's still the same reaction. So regardless of what that base is or exactly what the reagent looks like if you can put the reagent in the big bucket of Horner-Wasson-Edmonds reagent or Wittig reagent or whatever reagent, then you can go, oh, I know that is going to do this type of reaction if I have a base around, right? So I think for a lot of you, maybe I didn't do a good job of making that clear that, these things, they might change some, but at the end, they're still in the same big bucket. And looking at the reactions as like this reagent or this set of conditions does this thing. I can change things, but like if I have reagent and acid and ketone, I'm going to make this thing. So it doesn't matter what the acid is, and I can change the ketone, I'm still going to make the same thing. It's like looking at the reactions as being in like big buckets of this reagent does this thing, as opposed to this exact set of conditions does a thing, right? Because in organic 1 and organic 2, this is what I'm doing in organic 1 right now, so this is what I've heard, right? This is, oh, hey, double bond in this exact thing always puts halogens on your double bond. Cool, right? But now, we have, a different, it's like, okay, I can do a Wittig reaction, right? And I need a base. Doesn't matter what the base is a lot of times, as long as it can do the reaction is good enough. So if in one example it's N-butyllithium, and another example it's, LDA, another example it's NaHMDS, at the end of the day, these are all strong bases. So they're still going to allow you to do the reaction you want to do. And so just because you don't see exactly the exact same set of conditions doesn't mean that the reaction's not going to work like you have seen it work in the past. So try to look at the reagents as like the reagents, let it be Horner-Wasson-Edmonds, Wittig, the palladium reactions, as like big bucket, these things do this. And then the other things around it, the base, the solvent, the different additives that might get added, are improving that reaction or making it work better, but not changing what it does. So, right, big picture, you need, right, so you had bromine and a boronic acid, right? And then you have palladium, detritus. I kind of wrote it backwards, but right, you're going to do a Suzuki reaction, right? But what do you need? You need a base. You need some sort of, usually MOH. Right? This could be lithium hydroxide or sodium hydroxide or potassium hydroxide or cesium hydroxide. Right? It could be any of these as long as it has that base. And the solvent could be THF, it could be DMF, it could be acetone, right? It could be any number of different solvents, but like big picture, the reaction is a vinyl or aryl halide and a boronic acid with palladium, right? Even here, I had palladium tetrakis. This just needs to be palladium that's in the zero oxidation state, right? Or just, right, we did it in lab. We did it where we started with palladium 2, and it became, during the reaction, palladium 0. So as long as there's halide, boronic acid, and palladium, and a base around, you're going to get this reaction to happen. And the knobs that get turned by someone like in the literature, changing a solvent, adding an additive, like, makes the reaction better but doesn't change it. So try to I kind of identify the kind of bare minimum that a reaction needs to function. And when you see those pieces, realize that, okay, I'm doing this kind of reaction, as opposed to being well, these things have to match up. And maybe I did a bad job. Maybe I should have done a more generic example for everything, where it was just you need a halide of some sort. You need a boronic acid. You need palladium. And you need base, OH minus base. And that does a Suzuki. And then did examples where those things were filled in with more detail. Where it's this particular Suzuki, they used this palladium source to start with. They used this base. They used this solvent. I'll put solvent on here as well, right? As opposed to giving you the more specific examples, because I think a lot of you locked in on that for some things, and just well, I haven't seen this exact thing. So that's kind of on me. Some of the stuff I was confused by, the number 3, the one with the zinc chloride. A lot of you just missed that by 100,000 miles, and we're oh, methyl groups direct orthopara, and it's well, that's not what we're doing. You were kind of mixing reactions. But hopefully going back through it with some more time. That's another thing. And this is something you guys can tell me, right? Is we've got to do one more of these. Right? And a final. Ooh. Right? Was 2 days not enough time? Should I have done what I ended up doing for the second go around and been here's a week? Was it just an issue of time, where if you would have had more time to go through the thing, to go through it, you would have gotten more done? Or was it just, it wasn't an issue of time, it was you just didn't know what to do? Would have 3 more days just been 3 more days of sadness? Or would it have been 3 more productive days? And again, if you want to tell me now, if you want to email me or something, just because I need some feedback to. Okay, go ahead. Like your thought. Okay. 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 Like I said, I'm trying to make it better. I don't want you guys to I just want you guys to, understand stuff. I have more stuff made for going forward, but I would much rather get through less and have you understand more than march through a bunch of stuff that you guys don't understand, because that doesn't do anyone any good. No one's telling me how far I have to get, so I can kind of do whatever I want, right? So in that regard, we have some freedom. So I can do more like generic-y stuff. This is bad. I had a whole bunch of slides made, and now I don't know where they are. Panic, panic. 1 second. Like just like the hey, do this kind of thing. Yeah, yeah. Well, honestly, um, I should have perhaps been a little bit more worried because I put that the oh okay sir I put that together thinking that it would take like 15 minutes to go through like all 8 of them, and it took us 15 minutes to go through like 3 or like 20 minutes to go through 3. And something that I'm going to use 2020 as an excuse. Something that I'm having a problem with is like when you guys are in class and you're lost, you make funny facial expressions, and it's easier for me to be like, oh, this person doesn't know what's going on because they look like they drank sour milk, right? And I can like maybe re-explain something, but like I'm not getting that same kind of feedback. So like I can do like more. I could do something like that kind of at the end of like the slides and be like, all right, how do you do this thing, as opposed to like how do you do this simple version of this thing, and to get everyone kind of make sure everyone's on the same page. Like that's something I could totally do. Like because I haven't been doing what I did like in Organic 1 or 2, where I was like, all right, how would you do that? I'm like 95% sure we got there. Because the last thing we talked about was the Simmons-Smith cyclopropionation, right? So I vaguely remember drawing how that works. Right, so not trying to put you on the spot right now, but right, this is the Niori. God, I lost the ability to spell. Hydrogenation, where you need BiNAP and ruthenium chloride and H2, right? And a lot of times, right, if I was like, what are the conditions? You wouldn't even have to put like the solvent or random additive. Like this is the business part of this reaction is the ligand, BiNAP, right? And it would be R or S, but I don't know. Right? You'd have to actually run the reaction, but you're like, oh no, I do it in Niori. I need BiNAP, I need ruthenium chloride, and I need H2. Like that would be enough for me to be like, okay, you kind of know what's going on. That would be. So a couple of you, like, I don't know, whatever. It's a homework assignment now, basically, right? A couple of you, right, for the reaction that was, hey, whatever this is, right? Make a diol, right? And some of you were like, oh, we could use cold dilute KMNO4, right? Cool. And yes, you are right. It will make a cis diol, right? A cis vicinal diol. But right, we're trying to make like 1 enantiomer, right? And so it's like, oh, we talked about how you go from a double bond to a single enantiomer of this, right? Right, so this, or I should specify this right here, this is racemic, right? Because this is achiral, right? It has no chiral centers in it. right? Or it has a chiral center, but it's not set. This is achiral. So when you mix two achiral things together, you get an achiral thing out, right? And so we spent a lot of time talking about like, oh, you would use a sharpless dihydroxylation, right? You'd be like, oh, I need to use AD mix, say alpha, right? Right? This is still achiral, and now this is the chiral thing. So now I'll make one enantiomer. So now I only get one enantiomer of this. Oops. I can't write at the bottom of the screen because then it tries to pull stuff up. Right? I make one enantiomer of this because I used a chiral thing to make to add my alcohols. Right? So there's stuff like that where, you guys did the right thing from like organic 1, organic 2, but then didn't like use the stuff that we had used in here. And again, I might have done a shitty job of asking the question, right? You guys might not have had enough time to go through all of the stuff we'd gone over to like go find that thing. I don't know what the situation was. I will try in these last 6 or 7 lectures, in the words of Melania Trump, to be best. But I will try to do better going forward. So what I had planned to do even before the exam was we'd done the Simmons-Smith stuff, right? So actually moving on here. So you remember the Simmons-Smith cyclopropionation, right? And that was, you have a double bond and you can add diethyl, the way that everyone does it is diethyl zinc. There should be a 2. It's just a travesty. Diethyl zinc. Diiodomethane. And that's basically it. And you get, I made an epoxide the last time too. You get a cyclopropane, right? Where this carbon right here of the diiodomethane ends up being the carbon that's on the tip of the cyclopropane. And there's a couple different ways to do this, but basically it all comes down to, again, do you have some source of zinc, and then usually do you have diiodomethane? So, right, the actual Simmons-Smith is like zinc mixed with copper and diiodomethane, right? The one that everyone uses, or most often, is this version, right? So that was, I think, the last thing we were on, right? And we had talked about, ever so briefly, right, we're going to flip screens real quick. There you go. Like these examples here, where I have a double bond, I have these conditions, right? I'm not going to worry about the solvent, right? The solvent, again, this could be benzene or toluene or whatever it needs to be, right? Again, the part that really matters is you have diiodomethane and diethyl zinc. Like those are the two things that matter. That's what makes the reaction happen, right? And then it's like, oh hey, I have a double bond, and I think we talked about the stereochemistry here. The way you can think about this is, you've got this methyl group right here is down, which blocks the bottom face of the molecule, and this dot right here, that is how you can that is another way to draw a hydrogen as like a wedge. So as opposed to like trying to squeeze that wedge in between where the two rings come together, you just put like that dot, and it's kind of saying like the hydrogen's sticking up at you, like you're looking down at the hydrogen. Right, so then you've got hydrogen up, which means this thing here is down. So on either side of this double bond, you have methyl group down, this part of the ring sticking down. So this reagent comes from the top side, right, because that's the open side, to make your cyclopropane. And then I think I ended on like the charrette asymmetric thing. So here, this zinc, so I can actually draw it out here. Quick, to the other board. This is another thing, and like I am super guilty of this. Like, I don't know if it's like lazy or I just don't like switching back and forth. So I think there are times where maybe I should have switched back to draw something that maybe I didn't. So I will work on that. So like here, they have zinc CH2I2. This is kind of what happens when you have zinc, diethyl zinc plus diethylmethane. So basically you kind of mix these two things and you get this guy. But in the end, like you still got a zinc hooked to a carbon that has an iodide on it. And that should be like, oh, zinc and a carbon with an iodide on it. Okay, maybe I should think about that being a cyclopropanation. Okay. So there are a lot of times that reagents are close but not quite. And you have to kind of look and go like, well, where have I seen something similar? Like, okay, I have zinc CH2I. It's like, oh, well, that's kind of iodomethane, right? Or like try to pick up clues from like later in a structure or something like, oh, there's a cyclopropane here. Is there something that I can think of that makes me think like that could make a cyclopropane? It's like, oh, that reagent that we learned, right? I've got a zinc CH2 and an I, like cyclopropane, right? So, but what they're able to do is they use that and they use this ligand, which I pointed out before is a derivative of tartaric acid. Right, so it's the same ligand that you use like in the Sharpless dihydroxylation, or very similar. And this associates with the zinc and then lets you make your chiral cyclopropane. Now what I wanted to do, like I said before this, was I had put together, basically I found a synthesis of these apotholone analogs, where apotholone has an epoxide here, and they wanted to replace that epoxide with a cyclopropane. So if you remember organic 2, epoxides open really easily. If they're under acidic conditions, they open. If they're under basic conditions, they open, right? If you coordinate to that oxygen in some way, that epoxide is going to open. So if you give this as a drug, right, there's going to be a number of things that happen in the body that can open that epoxide. Right? But they wanted to keep that general shape. So they're like, well, if we get rid of the oxygen and just make it a carbon, it's not going to open as easily. Right? There's not going to be as many things that are going to open it in the body because I don't have that oxygen to put a proton on. And carbon's an even worse leaving group, really not a leaving group compared to oxygen. So that that cyclopropane is going to hopefully make it so that if this is a drug, it will stay in the body longer. So it won't get metabolized as fast. So maybe we don't have to give as much or dose as much because it doesn't break down as quickly. Okay. And at the end, they wanted to replace this with different heteroaromatic groups. So they wanted to be able to say like, hey, what if we take off this sulfur and we just have one nitrogen? What if we have two nitrogens? So like the last thing they did was they put in this group. But the synthesis overall, what I was going through it, I was just going to use it as like an example for a synthesis cycle for pronation. But the synthesis overall, I was like, oh, I think that like we can do like the whole thing. Like it's all stuff that you know. And there's a couple little reactions that you don't know that I can like teach along the way. So what I did is I did this in the, I don't know, most traumatizing way possible, which is synthesis problem. And I was like, we can work through this and kind of figure this out. And the thought process was there's a few things that you definitely don't know, like the thing from G to the product that's given, which we can talk about. But for the most part, like this slide, you know, like pretty much this whole slide from organic 1, organic 2, and what we've done so far. So I thought we could take some time and work through it. You know, maybe on a different timeline, we would have done this before the exam. But this is sadly the timeline we live in now. It has murder hornets, so it's clearly the best timeline. Oh, did you hear about that? In Washington State, they destroyed the first murder hornet nest found in the United States. Or was it North? I think it's the United States. They like vacuumed it out and put all the murder hornets in like little glass tubes.
It's terrifying.
It is. I was like, why are we saving them? Just burn them with fire. Like what?
I agree.
Like what? Like we're gonna like irradiate them and then send them to Russia? Like what are we gonna do? What I'm probably going to do is I'm probably going to draw a structure, maybe two, and then switch to the whiteboard. We can talk about what went on, and then I'll draw the next one, and we'll just slowly get there. Because, fun fact, not in a hurry here. Said I'd much rather you guys learn some, understand some stuffs than get through more stuffs. Right? I know. I'm leaving this up so you guys can like see the slide, and then and like you write some stuff down or whatever you want to do. I don't know how you want to do this, and then I'm gonna switch over to like I'm gonna have basically I'm going to have written up the slide or part of it, and then we'll go through that, and then I'll go back to this or I'll write up stuff. So I was just giving you time to write. Sure, no problem. I could also cheat here. Oh no, I'm not sharing with you guys. One sec. I want to get to something here. So you're gonna have to look at the small version for a second while I go to get to something. I don't know. Corey doesn't get to see anything. The joys of in class. So I want to find. Is this it? Cool. Okay. That's what I thought. Okay. So what I'm going to do is oops, I probably should not have drawn B. Start talking about it first. Okay, and then B. Okay, so first thing is we have an lactone, a lactone, and we're going to add methyl lithium to it at negative 78, right? So methyl lithium, if you remember, is a nucleophile, right? CH3, right? Carbon is minus, lithium is plus. That's going to add to the carbonyl carbon of our lactone. Now, negative 78, it kind of gets stuck. So, right, we're going to get doop, doop. Oops. Right, so it's going to add and then a thing that we are bad about when you look at organic papers is like, and we would normally write like, oh, we would add, right? We'd add H plus to quench the reaction, to protonate our alcohol, right? We don't usually put that in the paper, right? Because it's just kind of understood. Right? Have you guys gotten to sugars in biochem yet? No? Okay. So, do you guys remember what DMP is? It's organic too. It was in the alcohol section. And it was a mild oxidant. It was a thing that would oxidize primary alcohols to aldehydes or oxidize secondary alcohols to ketones. If you look at this, right, if you look at A, there's no primary or secondary alcohol, right? You just see a tertiary alcohol. But this is where the sugar question came in. Is if you have, so sugars do this all the time, right? This guy, that's a really bad TBS. This guy can open up. Sugars do this. They have their I forget the names. That's why I don't teach biochem. Right. And I'm cool. That's another reason not to teach biochem. Right. This can open itself up and go back and forth. So sugars do this. They have their aldehyde form where they're open, and then they have the form that everyone like normally draws as a closed six-membered ring, but they go back and forth. Right? This can do the same thing, and you can count. Make sure I'm not dumb. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So now when that opens, lo and behold, I have a primary alcohol. Now, the DMP, desmartin-pyridine, right, can oxidize that primary alcohol to an aldehyde. Oops, I forgot a C. Sorry, CH2. So right, you have, oh, I forgot a bunch of stuff. I forgot a C on the slide, sorry. C. He says C and writes F, so this is strong. To O2, there we go. All right, so as we were just talking about, we've got what kind of reagent? We have a Horner-Ross-Edmonds reagent. We have a base. We have an aldehyde. We're going to make a double bond. Right? Now, you have no idea what 18C, I guess it was 18C8, sorry. 18C8 is. Right? That's just an additive, does not impact your life. Right? So, we know that we're going to make a double bond with our, with this. So we know that this carbon right here is going to end up bonded to this carbon right here. And based on the structure after D, we can figure out what our stereochemistry is going to be. Right? So we're going to end up with, all right. Sorry, I have to go to the next slide. I only have so much space on my tiny iPad screen. If I would have known that this was going to be how I would have taught, I would have bought a bigger one. Right? So we're going to get now, I'm drawing it like it's on the slide. So I flipped it over. So the oxygen goes from back to forward, but that's just because I've rotated it around. We can check the R and S to make sure I haven't messed up if you want. Right? So, not that. It's not an H. It is a... Let me go back for a second. Don't yell at me. Oh, it's a methyl. Okay. So, right, it is... I'm going to share for a second. I don't know what you guys are looking at. Okay. So, you have this, right? Horner-Ross-Edmonds and a base, some stupid additive you don't care about. Still going to make a double bond. And if you're not sure what the double bond geometry is going to be, right? Because they're easy to predict when it's an aldehyde and just a Horner-Ross-Edmonds with no substituent here, but they're harder to predict when there's a substituent. You can find somewhere else in the synthesis, hopefully, like here, that's telling you like, oh, this methyl group in this chain are on opposite sides. So if they're on opposite sides here, they had to be on opposite sides when we made C, right? Because there's nothing we're going to do to switch those around. Okay. So also, if we look at B, let's go back to B, back to slidey things for a second. Boop. Right, B has an aldehyde and a ketone. Right, we learned in Organic 2, we weren't supposed to forget, that aldehydes are more reactive than ketones. Right, so we can just react with our aldehyde, and the ketone's not going to have a chance to react. The aldehyde's going to always react first. So that's why we can just say, like, aldehyde and ketone, do the Horner-Ross-Edmonds, it's only going to react with our aldehyde, because aldehydes are more reactive. They're easier to get to. Right.
Can you explain again why exactly like the substitution substitute, like the methyl group goes, or like,
So how I knew that going from B to C that C should look like this?
well, I just thought that because, do you have to have, for the fluorine, does that direct for the cis bond?
It does make it cis.
Okay, that's what I was.
Yeah.
That's what I
So you can, right? How can I say this? You're right. You could, just because it's the Stilgenari, the fluorine version of it. So the fact that this has fluorines, it's going to prefer to make the cis double bond. Which, if you look at it, the cis or like Z, right? This double bond here is Z.
Yeah.
Right. But sometimes, like, you may try to do this, and you might get a mixture.
Okay.
Right? So it is 100%, right? If you've got aldehyde and then just nothing on your carbon bond to your phosphorus here, right? That's going to make the cis double bond, right? As soon as you start putting stuff on here, right, that can mess with depending on how big it is, it can mess with the transition state and like how it's going to arrange.
Okay.
But yes, first principles, you should just think like, oh, I'm going to put the ester on the same side as the chain from my aldehyde,
Because
right?
if this like substitute's too big, then it can like not.
Then it can like flip it, or you'll get like a mixture. Because what you're relying on is the when the molecules react, this and this being different enough sizes so that it approaches in a certain way. The closer these get in size, the less preference there is. Because, right, so let's say that they're, if you bang it, like if you arrange, if the ester's on the right-hand side, right, let's say that gives you 1 kilocalorie of strain energy, right? But then if you put the methyl on that side, if it's like 0.9, that's really close. It's not going to be a big difference, so it's just going to kind of give you a mixture of the two, right? So as this group gets closer in size to your ester, you get more of a mixture, right? They also, like the additive, helped drive the selectivity to what they wanted. But you are right. Like the first principles is when you see this, put the chain and the ester on the same side of the double bond.
So, but basically, if like that little substituent, like little methyl, hypothetically was bigger than the other side, would it still make the cis conformation because it's so much bigger than the other side, or would it still be a mixture?
It could totally. So let's say you had, right? So let's say we had, or dumb example. So CH2, right? You could end up with, let's say this was really big, right? Say it was like tert-butyl, right? It could flip the selectivity to where now you get the other thing. It could flip all the way over.
So it can't do that.
Yeah. And then at that point, you probably wouldn't use this, right? Because that's fighting what you're going to get from that. You would use the other thing. You'd use just ethyl as opposed to trifluoroethyl. But it is, right, the selectivity is usually just a small amount of energy difference between two groups. So if they're close in size, you get a mixture. If one is bigger than the other, or one has a preference for approaching one way or the other, then you'll get that as your product. But yeah, like if you make it too big, it can flip the selectivity.
Okay.
All right. So then then I gave you no reagent, or no Yeah, no reagents, but then I just gave you a product. So C has an ester and a what's it called? Words are hard. An ester and a ketone, right? And then the product, after we do some number of steps, has an alcohol and the ketone's now an acetal. So if it's acetal, do you remember like what the role of an acetal is? So acetals, the role. I'm trying to say role. What they do, not rule. No, that's fine. No, I mean I am wearing a mask, and we are like you're on the moon or something right now. You heard there was water on the moon, and you were like, "Sweet vacation." So you're I don't know where you are. You could be on the moon underneath moon water, right? What do acetals do? I guess is a better thing to say, right? Acetals are kind of like TBS groups. They're protecting groups, right? They hide your ketone so you can do other reactions. So we have to hide our ketone so that we can react with this ester, right? Because esters are less reactive than ketones. So if we try to turn our ester into an alcohol, we'll turn our ketone into an alcohol. So we need to protect the ketone so it doesn't react, so that then we can turn our ester into an alcohol. So we already know what kind of, it's poorly drawn, but what kind of acetal we make, right? There's oxygen, 2 carbons oxygen. That means we need to have a diol that has 2 alcohols, and then we need an acid, right? Tosic acid or PBTS. Right? Then you remember how you turn an ester into an alcohol. Organic to you is very sad. Organic to you had this down. And then, like, a summer of stress and the Rona, you've all forgotten that. Yes, I need to turn an ester. I need to turn this ester that I have in green, circled in green, into this alcohol. Right, so this carbon right here is this carbon right here. So how do I go from an ester to an alcohol? That's strong. I would be super happy with that. Lithium aluminum hydride, and then some. Now, if you look at the paper, they use Dibol, right? But they both work. So if I were to give you something like this, right, you don't definitively know if they use lithium aluminum hydride or Dibol, but they both, from what you know, work, and I'd be happy with either. Right? So just because, like, sometimes there are like 3 or 4 ways to do something, and you don't know which one's the best or which one's going to work for your particular molecule until you try all of them. So if you were like, oh, I would try lithium aluminum hydride first, cool. That is a reasonable thing to assume that would work. It just does, so you don't have to. Right. Sometimes the right answer on paper is not the right answer that you'd do like in the lab. So just because we picked lithium aluminum hydride to try, and if you look at the paper, they use Dibal, doesn't mean we're wrong and they're right. It means they tried Dibal first, and they got like an 85% yield, and they were like, cool, I'm done. That is good enough for me. Or maybe they tried a bunch of other stuff, and this was the only thing that worked. So sometimes it's just, what do you end up like? Just because it's not in the paper doesn't mean it's not something that could be reasonable. Now, this next thing is the whole reason, literally the whole reason I have this, right? Well, no, not that thing. This thing, right? So, no, everything's green now. Right, so we had, right, so we have this guy that we just made. And do we have to turn that into, a cyclopropane? And I specify here that you only want to make one enantiomer of that, or one diastereomer, since there's already a chiral center in the molecule. So we talked about how to do that. Let me go back. Right, so that is this, where we would need to use a chiral ligand, and then I would just default to using the thing that they use. So I'd be like, oh, okay, zinc CH2I2, and then I don't know. I'm just gonna cheat and write Charette ligand. He's a good French Canadian guy. Right. And that would accomplish what we wanted to do there. Right? If there was another way to like make a simple cyclopropane that was chiral, and I didn't specify what way to use, if you picked that one, that would also work, right? Or that would be a reasonable thing to assume worked. A lot of times when we like propose a step in a synthesis, we're proposing a thing that seems reasonable, even though we know there are different ways to do it. So like when you do your synthesis project at the end of the semester that hopefully you've started working on, hint, hint, nudge, nudge, just because like you pick a certain reagent doesn't mean it's 100% right, but it needs to be a reasonable place to start, right? So now we have this guy. And again, I am calling on the powers of organic 2. Oops. I cheated you guys on an oxygen earlier, and I gave you guys an extra hydrogen here. Sorry. It should be this. So I have to put little quotes around it. I don't even autocorrect on ChemDraw. That's what I'll do. I didn't mess up. It was autocorrect's fault. So, what does Swern do? It will turn your alcohol into an aldehyde. Now that you have an aldehyde, whenever you see P double bonded to a C, you should think, I'm going to make a double bond? Resume share.
Oh, I thought you were asking if it was the search trans. That's what I did.
You're going to make a double bond.
I know that.
Okay, we're going to make a double bond. Zoom knows that too. Zoom's just quiet contemplation, quiet agreement. Okay, so Wittig reagents normally are trans, right? Are normally cis. But this is when you have an ester, right? This makes this a stabilized ylid, right? So whenever you have an ester or some other usually it's a carbonyl, so like a ketone, an ester, an aldehyde, an amide attached to the carbon that's double bonded to the phosphorus, that makes it so it prefers to be trans. So a Wittig reagent that is just, ethyl wants to be cis. A Wittig reagent that has some electron withdrawing group or something that has resonance wants to be trans. So we're going to end up with and we're going to make a trans double bond. That would be F. Now I have my F here. Make sure I'm drawing this right. I kind of am. So I now use Diebol, and Diebol only has one thing to react with, and that is the ester. And based on what our product is a little farther down, it's going to be an alcohol. So Diebol is just going to turn our ester into an alcohol. And there should be a double bond there. There you go. So that last reagent that I said you don't know, a problem that they had in the synthesis, it comes up a couple times, and this is like the first, is while cyclopropanes are more acid and base stable than epoxides, if you try to do hydrogenations or do things with palladium around them, they have a tendency to open up. So this last step right here, from the thing we just drew to here, the difference is you lose a double bond, right? And so they had to find creative ways to remove their double bonds in the presence of their cyclopropane. So normally you would just like be like, oh, I'll use like palladium on carbon and H2. But if they did that, their cyclopropane opened up. So they had to find unique ways to do hydrogenations. And this was their unique way. Again, I'm never going to test you on this thing because it is like super obscure. But sometimes you have to think outside the box and not just use the first or second or 15th reagent that comes into mind to try to find a way to do a reaction because your substrate is going to fall apart or is reactive in some other way that you have to like work around so you don't get so you don't have your thing fall apart. I think this is reasonable. We will stop here and we'll do the second and third slide of this on Thursday, and then maybe start on additions to aldehydes and predicting stereochemistry. And then from there, my thought was maybe doing more of this where I pick a molecule and try to find molecules that are using the reactions that we've already gone over to like kind of reinforce. And then like in this one, there's this reaction here that I can show you the mechanism for and how it works. And then I can show you this one here. So I can like kind of use them a little to introduce some new reactions. So I'm still teaching you some new stuff, but maybe we'll just try to go over things that you've already seen to make sure that's all stuck in your head relatively well. So if there are no further comments or questions, I think we'll call it here. Thank you. No, because I've got to take my car's car. My wife's car, I think she has a nail in her tire because it keeps going flat, so I'm going to go get it fixed at like 2 today. So I don't know when they're going to be done. So you get to just be free and like hang out at Starbucks or whatever. You never turn down a trip to Starbucks, man. It works out. Cool. Thank you. Okay. Bye. Yes, Jonah. I mean, I think the biggest thing that could help me is just like, so I'm gonna narc on Corey narking on you, which is apparently you guys like texted one day that you couldn't hear me and then you didn't tell me. So like if there's like a communication issue or like if you have questions or something, like please don't hesitate to like ask. Like, because like even today, like Corey was sitting in here and was like all like, participatory. But for the most part, like no one on Zoom said anything. And the problem is like I just assume if you guys are like not asking questions and not like butting in, that everything's cool. Right? So like I don't get the feedback of like the confused face or anything that like can like be like, oh well, they're not saying anything, but clearly it's not happening. Maybe, but like I don't know, like if people aren't comfortable having their camera on, I don't want to like force them to like have their camera on. So